Okay, welcome everyone. We are here for the Biochar and Local Carbon Network meeting with Paul Anderson, Dr. Paul Anderson. And my name is Amy McMorrow Hunter. I'm with the Climate Economy Education, Inc. It's a 501c3 nonprofit for education on lifestyles and business models that are good for the climate, economy, and humanity. And this event is part of our All Together Now Southern Illinois campaign. That's at alltogethernowsi.com. And we're having a number of educational events through April, and this is actually the last one. We're wrapping up April here today. And then next month, we're gonna be starting some new efforts to get people completing the climate SWOT and to start organizing some community listening forums. And we're just gonna be starting some new projects, hopefully too, related to biochar and local carbon networks like we're talking about today, and we're going to be carrying on with that. So this is a Tuesday at noon. We're going to be every Tuesday at noon from now on. We're going to be meeting and talking about local carbon networks, and every Wednesday at noon we're going to be talking about solar and renewable energy and energy efficiency and clean energy jobs and all that kind of stuff. So we're going to keep this going. This is the start, but also an ongoing conversation. So I thank you all for being here today, and I encourage you to stay tuned and participate. And I think that's all I need to say. So I'm gonna go ahead and run around and let all our attendees quickly introduce themselves, and then I'll hand it over to our speaker, Dr. Paul Anderson. So Tim, do you wanna go first? Tim Michaels.
My name's Tim Michaels. I have an energy consulting firm. Started it in 1975. So we've been chasing BTUs and watts for quite a while. And that's what we do. And we also try to promote sustainable job economic growth and things like that. You know, we've done lots of projects across the country. Thank you.
Thank you, Tim. Joyce.
Oh, excuse me, Tim, could you tell us where you're located, and everybody could please indicate more or less where you are in the country?
We're across the river from Illinois and Missouri.
Okay.
The east side of Missouri.
Okay, Joyce.
Yeah, Joyce Harrent. I'm in Peoria and part of the Central Illinois Healthy Community Alliance and Illinois People's Action. And I'm here to learn.
Thank you for joining us, Joyce. Aaron.
Hello, I also work in St. Louis with Tim at Energy Resources Group. Mostly, yeah.
All right, thank you. Sally.
Hi everyone, my name is Sally Burgess. I work for Sierra Club. I am an organizer who works in the downstate area, and I am located in Edwardsville.
Thank you, Sally. Glad to see you here today. Sonia.
Hello everybody, my name is Sonia Kruger and I live in the Carbondale area here in Southern Illinois, and I'm joining today to learn more about what all of you do and carbon sinking solutions for the future. And I am the project director for the Southern Illinois Cooperative Business Fund, moving along cooperative culture and worker cooperative ownership within our region. I'm happy.
Thank you, Sonia. Brian.
Brian in Western Washington State. I've been dabbling in making biochar for 8 years and 30 years running chainsaws and doing tree work, both residential and in the woods. And I'm fascinated with why this biochar, which seems a win-win, is not making any traction. And I have a few theories on that, but we'll just let that go for my introduction.
Thanks, Brian. All right, Andrew.
Hi, everyone. My name is Andrew Hagan. I'm an engineer at Energy Resources Group, along with Tim and Aaron, and obviously St. Louis as well.
All right, thank you. And this is a pretty low-key environment. If you have a question, you can either put it in the chat or just chime in, turn your microphone on, and ask. If you want to keep your camera and your microphone on, that's fine. And so for now, I'm going to hand it over to Dr. Paul Anderson.
Thank you. I'll introduce myself. I'm Paul Anderson, and I live in Normal, Illinois, and I am a retired professor from Illinois State University, but I've been retired for 18 years. I have had more months after retirement than I had actual months of employment at Illinois State. Before that, I taught in Brazil and I taught in Australia and places around the world. I got into the issue of biochar because of cook stoves. I got involved with the, this is 20 years this coming month. I met a man who was an expert on what became known as the Tila gasifiers. Changed my life. I've worked on it because these stoves make charcoal or biochar. I got invited to go to, I got interested in going to the biochar conferences, and because of the biochar conferences, I've been involved in the climate crises types of things. So I've got a number of things that I deal with on that. So let me shift over to my share screen. I found the right thing here. Not share screen and share. Oops, did it? Okay, just 1 second. Bear with me. Presentation. And are you seeing it now or not yet?
Not yet. Did you hit the share screen button? The green share screen?
I did, and now it's no longer available for me to see that. Show taskbar, no.
Do you have the Zoom window open and maximized in the screen, and then you can see all the buttons along the bottom?
I am going to, I was on this before, and my apologies. I'm going to exit out of that one because it's overriding my whole screen. So I have screen share button. I can see that one now. I push that. I have to
Choose the window.
the window, but the window that I have needs to become maximized.
Okay, you're sharing your screen.
Now I go to the share that. Okay, I have to go this way. Slideshow.
We can see your 4 ways to pyrolysis to be profitable.
Yeah, and that, okay, I'm on slide 2. That's all right. I got my controllers over here. All right, and it's filling the whole screen, correct?
Yep.
All right, fine. Tentative title, as we said, this is very casual.
Yes.
I met Amy, what year was it, Amy, you had your conference?
Well, it was 2019 in Carbondale, June 2019.
June 2019. Gee, it seems like longer ago than that because of COVID. But went to Carbondale and got very enthused about the different types of things. I explained some of the stuff that I was doing there. Lots of things have changed since there, so this is certainly no repetition of what I've done in the past here. There's my email address. I'll give that to you later on if you need it. The 4 possible ways to make pyrolysis profitable. The one, obviously, charcoal products. This is the biochar, but if it's the char only, it probably isn't going to make enough money to be sustainable. We'd like to use the energy, and it's mainly thermal energy, not trying to talk about electricity all the time, and which is the big buzzword. Everyone wants to do electricity, but just the thermal energy has great value. Biomass disposal, out in California, they've got to get rid of the underbrush in there, but we've got landfill issues, we have air quality issues, how to do it cleanly. And the other benefits, the chemicals, the derivatives that you can come from it, the carbon offsets, which are marketable, and then of course the climate benefits that just we want to help the climate come out. They are actually, that's different from the carbon offsets or the carbon removal type of issues. So that's how I usually start off things, to put things into perspective. We want to get 1, 2, or all, 3, 4, all of these working together to make something to be sustainable. This slide simply says objectives, to make and use biochar locally. Amy's the driving force for Southern Illinois, and I'm up about a 4-hour drive away. And actually, Joyce, you're only an hour away from me, and we'll talk about stuff. We'll probably meet with fairly soon. I hope so. And one of the objectives here is there going to be a nucleus, a focal group, activity centers, something in Southern Illinois, or virtually in Illinois itself? The Illinois Biochar Group exists, it functions. COVID has put the dampers on it, but I am one of the 2 guys that founded it, and we've had meetings in the past and look to have them again in the future. So if I can help out in the biochar way, please let me know. Okay, I give here 2 websites. My one website is Dr. Tlud, D-R-T-L-U-D, drtlud.com. I didn't invent it, but I did name it. And this is the technology of a migratory pyrolytic front going down through the biomass. I should almost ask for a show of hands of how many people are aware of it, but it's not the main focus today. I will introduce it just briefly in there. And the other website, I have a new company formed called Wood Gas Pyrolytics. So woodgas.energy, and at the /resources, there's a whole bunch of documents that you can look at, some videos, things I'll be referring to. There's a place that you can go back to for some of the materials and backup things, and maybe some of the materials that we have today will appear there also. On the TLUD type, stands for top lit updraft, and FA stands for forced air or fan assisted. And the fab stove is not just fabulous, it is a forced air base. Okay, that's where the name originally came from. But the fab stove is made in South Africa. It is now imported into the United States. Full disclosure, I am part of helping the guy in the operation in South Africa, and I am instrumental in helping to get these units to be available for sale in the United States. The sales are handled by Mike. His website is blueskybiochar.com. I recommend that site to you for if you're interested in the the nutrient characteristics of biochar. You're interested in wood vinegar and those types of issues. He's got good videos and things. The unit from South Africa, he's selling it at $189. Got some shipping on it, but it's just arrived in America within the last couple months. Question?
Well, can you say his name again? I lost you there for a second.
Michael Whitman, W-I-T-T-M-A-N. No,
Thank you.
Michael Whitman. In this stove, the red base has a fan underneath it, and it is run with 5-volt power, which is coming out of the battery pack. The cable's not shown, but it plugs in a USB thing, the same as for running your cell phones and stuff. And the pot sits up on top of that stainless steel, the pot rest. Now, there is a coupler, a little telescoping thing that will join the upper part with the gasifier, which is the one in the center, the silver. It's a mesh outside. It has a wooden handle on it. and it burns pellets inside of that. Extremely clean. I could go on a lot about this, and it will produce very good biochar out of the pellets at the typical rate of about a 20% yield. Put a kilo in and you get 200 grams out, all right? And you can cook with it for about an hour and those types of things. If there's if there's interest in this as a way to make biochar, very small scale, that's fine. We can talk about it, maybe some group in Southern Illinois and all that. It's not, I would say, if the world is to be with zero new carbon emissions by 2050, all of the people that are cooking will be cooking with either with biomass or electricity. There'll be some solar, but not down at night. But gas and kerosene cooking and coal cooking and stuff will all be out. And so when you can have basically a gas burning stove that makes its own gases out of biomass, and it's very clean, then this is something which we would want to have. You use 1 watt of energy for the fan to get 1,000 watts of thermal power out of it. So it's a great device. I've got some here, and I'll mention now and other times, there is a likelihood that I should probably come down to the Carbondale area if Amy was going to sort of sponsor, gather together, and we might have a demonstration of this plus other stuff that I'll be showing today. So we're not that far away from this. And for Joyce in Peoria, happy to show it to you at any time. I mean, I've got one and we can cook with it. I'm not trying to convert you all to cooking with it, but it does make biochar. Now, why is this significant for climate? In the natural draft versions, not the ones with the fans, the natural draft versions, there is something like 100,000 of these units in India already, and each unit will produce approximately 1 ton of carbon dioxide equivalent as a removal per year. So this is, if you have 100,000 of them, you could get 100,000 carbon dioxide removal units. And what's been happening? The people are cooking with the same fuel that they used before in a sustainable way and using less of it and sequestering more carbon than most other projects can be produced in other ways. And there are, my target is 250 million households, and that's only half of the number of people who are households that are actually cooking with solid biomass fuels today. So it's a monstrous amount of energy and sequestration that can be accomplished. So to do something in Illinois with the cooking tool, it's something of an interest, or if somebody has interest with it. But I should mention that let's see here. Yes, there's also at the Dr. Thielud website a number of articles and things about pyrolysis in 55-gallon barrels. And I'm actually not going to focus on it because the barrels, although they do a good job of it, they're a little bit fussy. You need to have dry biomass. You have to pack it sort of the right way and stuff. And so that's what, after working on that since 2001, I have now gone into what is now the rock kiln, the rotatable covered cavity kilns, which I'll discuss next. So that's all I really have to say about the Thielud's. If you're interested in it, please, we can follow up with it, especially if there's a few people with interest, we can get together and we have it. Certainly, if we have an outing, we will make popcorn and other things on my Thielud stoves, the fab stoves, when we're together. Okay, rotatable covered cavity kilns. And the concept of the ROCC, R-O-C-C, is that the biomass goes into the chamber, it is pyrolyzed, and it becomes, and the gases come off, and the charcoal accumulates in the bottom. The next slide shows the same left-hand diagram. Get it right here. Okay, and on the lower left is the open top cavity kilns as opposed to the covered, or at least partially covered, cavity kilns. And these cavity kilns, you throw the biomass in, there's a fire, and there is no air entering anywhere into the bottom of this chamber. Sometimes they're cones, sometimes they're conical, sometimes they're troughs. You can do it as a trench in the ground, even it can use. And what happens is, as the pyrolysis occurs, the biomass is converted into charcoal, and the gases come up, and the gases are what's burning up at the top of in here, and oxygen gets to that, gives you the flame, burns it, makes it rather a relatively clean burning situation. And that oxygen cannot reach down below where the charcoal is collecting, and therefore you're saving this charcoal as it goes along. The disadvantage of this kiln is if you feed it too fast, if you just keep throwing stuff into it, you can actually bury some of your biomass underneath an area, and it is insulated from the heat. The pyrolytic heat is what's burning up above. It's insulated, so you need to go back, you need to stir it up, you need to bring the pieces up to the surface so that they will pyrolyze, and you'll get a good mix into there. So what I have done in the rock kiln is that the same process is occurring. The char is accumulating at the bottom, the gases come up, we're burning it, but the gases come in over the lip. They call this the porthole, the opening that's there. Comes into there, it's burning those gases, and it goes up to a chimney, or even without a chimney on it. So the that's fine. And I had that for several years without rotating it. So I've added a rotation, not rotating, but a rotatable thing for mixing. The main purpose is that you're able to mix the char on occasion. So here's a picture of some of the open top cavity kilns. They're more susceptible to the wind variations coming into it. There's less chance of capturing the heat from it, and you certainly have to either be there and stir it to get it in there. So they're pretty hot to get up close to it at the end. There's a limit. You obviously can't make this thing big, gigantic sizes, because you could never approach it in order even to be throwing the stuff in. Well, yes, there's a big, gigantic size. How about this one? I didn't do this. Other people have done it. This is the half of some gigantic metal cylinder, and they're using a bobcat or something here to be able to load it and throw that stuff in. Major flames, stuff coming off from there. And in the end, they're going to end up with charcoal down in the bottom. They will end up with some stuff which is torrefied, because if it's been protected, if it's been too much protected from the heat reaching it, they are not able to mix that and stir that. I would say this has not caught on, because one of the things is, after you make something this big, really the only way that they even extinguish this one is they rolled it and they flipped it. And so then you're ending up with it upside down, and you're sort of suffocating the char that's inside. And I'm not recommending this. I'm just pointing out that this is the largest one that I've seen, basically making a lot of char. It's not an open fire on the ground, but it is very much an open fire. So this is the flame cap technology, which is used in the rock kilns, except that the rock kilns are partially covered and rotatable. I have an explanation which has been distributed. I can send it to people if they become interested in it. An X-frame arrangement. The green circle here is the rectangle that's visible here from the side view, is the barrel, and a 55-gallon drum. I'll show you some pictures in just a minute of it. It has a pipe that goes through the center. It could be all the way through, or it could be just axle stubs at the end. You don't have to have the pipe go all the way through. I've done it both ways. Handle on it to be able to turn this, and it will then pivot on a rudimentary axle, and they're not even bearings needed. It's just a pipe within a pipe, and we put wheels on it. You can pick it up and you can wheel this thing around, and again, you'll see some pictures of it. This X-frame design is one of several. You'll see some other ones here. Typically, now this is a barrel with a 55-gallon drum. The opening here straight across is 12 inches. It's 13 inches measured on the curve. This only has stub axles on the end of it, and it gives the dimensions. In the rock kiln design, the chimney or hood is represented up above into here, and you can have where the emissions are coming in and out and going up to the chimney there. You can rotate it upwards, and this actually limits the air going in. So it's a way of calming your fire to keep it from getting out of control. That the air, it will actually, you can almost put it out in there. Rotating it, the hood stays in a fixed position, rotated to the rear side. Now you even have a more clear shot at throwing in fuel into it. And the A, B, C, and then D for dump, didn't just nicely turned out that way, or down, is to empty it. And so the char will then fall out and you collect it into there. So these are the positions of the cylindrical covered cavity kilns, which can be rocked back and forth, or it can be actually totally rotated all the way around if you put a little door or some bars on it, which I can discuss. Some of the sizes. What you're seeing here, these two on the right-hand side are about 32-inch diameter. This was made in India, and it's just a little bit bigger because of the photographs with scale, you can't tell. These other ones here and that I'll be showing you are in 55-gallon drums, which are 23 inches, a 2-foot diameter. So it's sort of a 2-foot diameter versus a 3-foot diameter. And I'll show you a 4 and a 6 in just a minute here. So these show you a chimney effect. This one here is simply a sheet of corrugated metal with one chimney rising up from it. And you see it also down in this picture into here. We're feeding in the fuel from one side. The fuel gets dumped and comes out a chute to get it away, or it can dump it straight down. So this is the essence on it. These units here, you are seeing, I'll point it out in this, you see my cursor there? I'm moving it. Is that visible? Can you see the cursor on the middle picture in the bottom? No.
I don't see it.
Oh, it's not, okay, I think I'm pointing this stuff and I can't point. Oh, wait, I gotta go into this one over here. Now you can see it there, right?
Yeah.
Okay. I point, but now I turn this way. Now I'm looking at my other screen, so now you can see it. Okay, crazy. All right. This has a frame with 4 wheels on it. You can see the wheels over here. And this barrel then rolls on the wheels. It does not rotate on an axle. So we have the rack with rollers, and we have the axle as ways that we're able to do it. All of those that's shown in these pictures are that way. Okay. This comes out of a different slide presentation I've done with regard to searching for the sizes and things. Up in here, these are the cook stove types of things that we're dealing with. And there's the big ones down below, the big units where you can pay $250,000 or 100,000 or multiple millions to get a pyrolytic device that's going to maybe also make electricity and the rest of it. What's been missing is stuff in the midi and medium scale in order to produce I classify it as in 10 hours of operation. An extended work day, good work day, you're going to get 100 kgs up to 1 ton of finished biochar coming out of it. And then next, these are all in orders of magnitude into here. Medium would be 1 ton up to 10 tons, and then you go larger up into there. No, I'm sorry, I misspoke. This is on the input of the biomass. If you're putting in 1 ton of biomass, you would expect to get out 200 kilos, a 20% yield of biochar. Typically, a 20% yield is what we're looking for. So this, I put this slide in because it shows a rock and roll barrel kiln processes approximately 25 kgs, that'd be 55, 60 pounds per hour, or a quarter of a ton in 10 hours of operation, yielding 50 kilograms of biochar. This is not big numbers, but if you're doing it by yourself, or if you're doing it on the individual scale or a small little group of people, this works out fine. Now, if you have 10 of these units working and they're all doing it into there, you would end up with 500 kilograms of biochar, and that's more than 1 carbon sequestration unit per day. So we do the numbers on it in a number of different ways on that. Okay. So, okay. Now, some of the units done in Kenya. This is with the that X frame that was mentioned earlier, showing into there. And this was made out of a barrel, and pretty much most of the rest of it was scrap. So when people are saying that, hey, can they afford to make it? If you went and bought new material at Menards, it still isn't going to, or Home Depot, it's not going to cost very much. But they found stuff in the local yard, some straight bar. This is like a 1 by 1 inch hollow tubing. This handle here was the arm off of a chair that they found. And then they since put on another arm down below, so they have 2 of them in there. And it's pivots on there. They did some welding, put it together, and made this frame so it would work. And then they've got that set up. The first time that you use one of these, you definitely are doing it just to burn off the paint, burn out any contents in it. Don't, stay away from the emissions and stuff. A series of pictures from some different ones which I have made at different, this is one operation, but several pictures of it. It's flaming away into here, and it's going up pretty much up through the chimney. Yes, it can be smoky if you're not careful, and if your fuel is wet, you want to be alert to that. You can see I put some fairly big chunks of wood into it, and they were pyrolyzing. This event was about maybe 2.5, maybe 3 hours for these pieces, and they're all pretty well disappeared. Coming down, you could continue putting fuel into there until you filled up halfway full with your char. And you don't really think of going much more than halfway full, but you can keep putting in the material and rotating it to mix it up and stuff until it's pretty well full. And then here I'm dumping it out just down onto a catch pan and the stuff that comes along in with it. So it works. It's been done, the testing and stuff with it. This is from Kenya again. The last couple was in my backyard. This is in Kenya again, one of those, the units, you see the handle's got 2 things on it now. They fixed that. And the picture on the left does not have a hood in place. And we have found that you can work very nicely without the hood. If you, especially if it's not too windy, the wind, it helps if you've got the, if it's windy, it helps if you have the hood. And so the one on the right shows a hood in place. And here is they've dumped out their char. They collected it on a metal tray, and just to catch it into there. They are burning straw out of, I think it's a rice field that was in there. This is just done within the last week or so. This diagram shows you then a concept on how to clear off the surplus biomass of fields. There, you can, it's dashed lines. The cylinder is not very evident in here. The cylinder is this part into there, and it has the hood and stuff on it, and wheels on the end so it can be pulled through. Think of it sort of like a rickshaw, and you can pull it through and just keep throwing your fuel up in through there into the into the part and then rotating it. So I've got that type of thing. This is the example that I built at home. It works. It has its design limitations that I'm still working with. One is there are actually 3 parts that could move separately. The barrel itself, which sometimes you want it to be fixed position, sometimes you want to be able to turn it by itself. The blue here, they're on here upside down. These bars are what are holding up the hood when they're turned the other way, and the hood arrangement is supported up above it, and you don't want that to try to spin around on you. And then finally, there's the outside wheel so that you can actually wheel it through the field or across your yard or whatever else you want to do with it. So in a work in progress as a rock kiln that is that's designed to roll, what do we call it, longitudinally, I guess, or the other one had the wheels crosswise on it, and it was more like a wheelbarrow. Okay, so go to next. There it is in use, and again, it's in my backyard. I live in a typical residential situation in an Illinois suburb, so it's I've never had the fire department come on to me for any problems. I haven't had neighbors complain, although I have to admit, I've had a few smoke incidents, which you can't leave it go unattended, of course. This is an experiment from, I think it is 2 days ago. One of my predecessor units was the heat source, and I put the rotatable barrel up above as a dryer. One of the big issues is how can I get my fuel to be dried more than it is normally and dry it faster, and then to dump it into the other unit that's down below. And this is just put up with rigged together with some concrete blocks and stuff. This is definitely the work in progress. But you're able to then dry. It did not transfer the heat nearly as much as I thought it would. The idea is if you actually had the lid over this top part becomes a retort, and you have to have a hole in it, obviously, for gases, the moisture and stuff to come out. And you could make a retort type of char. But retort chars tend to be lower temperatures than if you're doing it with the flame cap, because the flame cap has flame present. It gets much, much hotter into there. Work in progress. Again, I say that so that you all know that you're invited to participate in the progress, okay? Backside there, the yard, just looking at, again, the same basic setup. A diagram for a 6-foot diameter cylinder, so I could stand up, any of us could, unless somebody here in the group is really tall, you can literally stand up inside that cylinder, and it's inside of a 20-foot shipping container. And here it rolls on a rail, on 2 rails in the bottom. It is not rotating on the central pivot, and it is not rotating on rollers in one spot. It actually rolls inside of this container. So this unit now is next picture. It's been built and it's being refined as we work on it and stuff. This is from the one on the left is the back end of the back end of the unit. You see the power drive. This is electrical driven. It's got a motor into it to rotate this drum. The picture on the right here is a 20-foot shipping container. This is the fuel receiving end. The other picture on the left is where it's ready to dump the char down through the hole that's in there. There's a couple more pictures coming onto here. This is, I mean, it takes a lot of fuel going into it, burns it very nicely. Here's the flames coming through. We have not put any chimneys up above on it. We're working on mechanisms for how to load it, and there's conveyor belts and things like that. You don't think you're going to operate this thing with manual labor in Illinois. You might have something large like this in an overseas country where labor is very, very cheap, but this produces a a great deal of heat and great deal of char. One, as in my first slide, if you can use the heat, the char is free. If you can sell your char for enough, the heat's free, just whatever you want to do with it, those types of things. So here's some more pictures of the one on the left is at the receiving end where fuel is being put into it. You see that there's no flame on the lower lip here. The flame is going underneath this upper lip and then going into the places where the chimneys would be up above. In the photo on the right-hand side, you see that the cylinder is rolling on these rails, big 4x4 steel rails. It has been rotated back. The wood falls inside of there, falls over on top of itself, breaks itself up, continue to roll it, and it will actually dump it down through this hole into a container that we have underneath it. Okay? Is this a finished product? By no means. Is it a proof of concept and how things work? Yes. And it definitely could be something of substantial interest. And I'm not saying that it needs to be in the container. The container limits it to a 7-foot width of that cylinder. But we can rotate this cylinder the other way and put it either on the rollers or on the central axis for rotation that way. Similar thing. And I want to be able, and we can make these chambers 20 feet long, the cylinders, 40 feet long if you needed to, and I don't imagine that happening. You see that this is corrugated steel. This is what they use for culverts in North America. There's 30 different factories around the United States, many of them in one company, but that are producing these culverts and selling them off to who's ever doing highway work in other places. And you can get them in I think up to, I think you can get a 16-foot diameter, maybe even an 18-foot. I mean, it's gigantic, and you can have it 20 feet long. I mean, you're going to be loading this thing with forklifts and dropping in long things. Like one of the issues is bamboo that might be 20 feet long. You want a cylinder that's 25 feet long, so that you just hit that hole nice and easy and it goes right in, feeding it massive amounts into there. So these are, again, the options and things for such developments. Here is at the working end before it's been, this is the size of the wood we've been throwing in. A lot of these are 4x4s, comes out as a nice biochar. This is from a waste recycling facility, which is here. Joyce, you ever drive over to Normal, when you're at the Goodfield exit, look to the south side, and you'll see this white building here, tall, 70 feet, 60, 70 feet tall for Chip Energy. And here's the pile of the waste wood, which has been, they pay Chip Energy to receive this wood so that it doesn't go to landfills. And it represents, I mean thousands and thousands of tons of biomass that has not gone to landfill and is going to be either made into biochar or it's going to be made into fuel briquettes. This is part of the Chip Energy business model and stuff that so this is where I get these units built. Paul Weaver, a friend of mine, I'm involved in the business arrangement also with Chip Energy, and we are able to work with biomass, and we can work with the various issues. So that's all the slides which I have specifically designed to put out. Although we can go back to some of them, we can add other questions and things about it. And check my time here. Yes, we keep it going. We want to talk about some of the options. My question is, if people are wanting to do in Illinois, central and southern Illinois, or out in the state of Washington with Brian, you wanting to do a project and things, I can help you get the equipment so we're up and doing it and that type of thing. but somebody has to be operating it, running it, putting it, going to use the char, marketing the char. I also can deal with when there is char that is produced, I am able to, we have a way of with blockchain documenting the processing of it so that there can be trustworthiness, confidence that it is a true sequestration. And true sequestration is now being marketed at, well, Microsoft has bought some at $80 to $120 a ton of CO2 equivalent. So, and I want to conclude one thing here. If you're going to do something about biochar and you want to go with it, I calculated out from a sample I have here, you can get about 33 kilograms, that would be about 75 pounds, of biochar into a 55-gallon drum. You got to think of how much you're going to get out. This is bone dry, no moisture in it at all. And 5 barrelfuls is a cubic meter, 4 barrelfuls is a cubic yard, okay? And so there's about 33 kg. I do the metric system because it's CO2 equivalents are easier. If you're 33 kg of charcoal, biochar, in a barrel, and you would have 10 barrels, 2 cubic meters, 10 barrels to give you 330 kilograms, and 330 kilograms with the transfers and the allowances and stuff is going to give you approximately 1 ton of carbon dioxide equivalent. So if you're going to produce charcoal, that's going to, if you want 1 ton of it, and Microsoft says they're going to buy it for $100 if it's truly sequestered. You don't even have to give them the char. You just have to prove that it's been sequestered. Somebody else, you still get to sell the char. You use it in your gardens and everything else. But you need about 10 barrelfuls for that. So if you're going to be doing it in small bucket cup amounts like that, it takes quite a while to get you to the amount where we're up to a sort of, I don't want to say it's all measurable, but to where it's appreciable. So I better let some comments come in, and I would like to hope that people would chip in with some quick comments of, well, that was boring, or this is exactly what I want, or something. I mean, I don't know. I'm hoping somebody's going to say, yes, let's do something in our local areas and how we can make it happen. Thank you. And Amy, you'll moderate this so I can take a breath.
Yes, thank you, Paul. And we have had some questions roll in, and it's 12:54, so I'm gonna run this about 5 minutes after the hour for everybody that has to go, because I know some people will have to go at that point. But if you can stay, we'll stay after that as well. So, but I did want to address a couple of the questions that came up from Hillary here. She's got 2 questions. Is there any solution to address the smell?
What smell?
Is there no smell? I mean, what is, when you're doing this properly without the smoke issues and all that, what is coming out? What is it?
I mean, I mean, smoke is smelly, okay? But we're trying to do it without smoke. I'm surprised at the word smell. I would accept, what about the smoke, okay? For the most part, we have a pretty clean burn, and so you're not smelling very much at all. But if you've got some smokiness coming through it, it will smell like smoke.
Okay.
The char doesn't smell. The char will actually absorb odors and things. You put that into manure and make your barnyard smell better.
Have a tested business model.
Say again?
Do you have a tested business model?
I welcome all of you to participate.
Exactly, that's what we're working on, right? Well, okay, so what cost of that system? Let's see, maybe Hillary, do you want to jump in and
Yeah, I'm sorry, I was typing fast. So what's the cost, let's say, of that system, like the 10 barrel to produce the 330 kilograms or the 1 ton of CO2? What's the cost just for, let's say, that particular system?
Okay, first of all, the 10 barrels full of thing is a cumulative result that you could get it from either using that little cook stove if you used it enough times, or you use the barrel size, or you use the giant 6-footer. So they're all changed into there. The barrel size one, as I said, with some scrap material and stuff for a few $100 and a welding friend or somebody, you can get one of those up and have it to be able to use it. The larger units, actually the one which was at the very first, and there was the 4-foot unit. I mean, we're talking the prototypes and stuff, we're talking $6,000, $8,000, $12,000. I mean, the one in the shipping container I'm welcoming any investors, is costing a bit of money. So I don't know, do you want to make it yourself, or how do you want to
What's a bit of money? I want to get an idea of what the capital expense for this, so that we can project what the revenue would be, right?
If you want to make a unit which is of the substantial size, 4-foot, 6-foot diameter into there, you should probably be budgeting somewhere close to $10,000, which is a fraction of what you would pay for, you know, what if you're going to have it with continual rotations and the other types of stuff.
Okay, we have another question. What are the gases emitted?
If it's burning it cleanly, it's CO2 and water vapor, okay? If it is not, you're going to end up with some smokiness, some particulates, and you get some carbon monoxide in it, but most of it is CO2. We're doing it outside, so we're not going to have, you know, emissions of, I mean, you might end up smelling smoky, but you're not going to get carbon monoxide poisoning from being in the smokiness. If that were the case, we wouldn't be sitting around campfires. So
But the idea here is that we're reducing carbon dioxide emissions through this process. We're sequestering.
Okay, yes, the good point here. If you grow it, if a tree grows and it takes the carbon dioxide out of the atmosphere, that's fine. If it rots and goes back, it's giving you CO2 back, it's carbon neutral. If it does it the wrong way, you can get methane and stuff, which is even more damaging to the system. You put this stuff in it, it's emitting. So if you are able to pyrolyze and you put 50% of the carbon atoms back into the atmosphere, that's an emission, carbon dioxide emission, you've still kept 50% of the carbon atoms in the form of biochar, which has this long-term sequestration of at least, got to be credited with at least 500 years, and it should be credited in the 1,000+ years for recalcitrance, for being a permanent removal. So yes, it's carbon negative because it's in the net result, the charcoal represents carbon dioxide removed.
Right, and when we're talking about these types of situations, we're understanding that we have to kind of plan them out ahead of time and calculate these things and make sure they're going to be producing in a beneficial way and not actually causing more problems than it's producing benefits. So in any sort of situation like that, we're going to have to be considering how we're doing it, what sort of feedstock we're using, and how hot, and what do we want to produce, and all these things. So it's always like a process, I would say, to design it the best possible way. Would that be safe to say that?
If somebody is going out and cutting down healthy, good trees just to make wood that they're then going to pyrolyze and stuff, for the length of time that it takes to regrow those trees, it's the carbon positive, which is the bad way, okay, for it. But if you've got dead trees in your woodlots, if you're using the corn stover or surplus biomass off of fields and things like that, you're carbon negative.
Right. So you have to be just mindful of the
Mhm.
situation. So Tim Michaels is asking, how can this be used in treating the organic fraction of municipal separated solid waste?
Hmm. I like the question, Tim. Part of the issues are that it needs to be dry before it goes in there. The second is that it does not work, this design does not work well if it's fine particle, it compacts in on it, it doesn't allow that heat to get down in and to pyrolyze it, okay? So that the, if you have a way of putting in the biomass in a constant, consistent way, fluffy, and just sort of spreading it in there, and the oxygen's there, and it's burning. It's almost like fluidized bed. It's almost like the this fast pyrolysis. Okay, it isn't fast pyrolysis, but it's in that nature. Okay, then it could work. But if you're just going to put a bucket load of dampish, municipal solid waste types of stuff in their sewage waste into it, it's going to suffocate itself, and it doesn't work. So if the solid waste is pelletized and becomes a fuel, you can actually cook your dinner on it, like in that little stove that I did. But that's extra money that goes into it. So I hope that answered. I'm not too sure. Maybe a further question?
Well, to follow up, what about things like plastics? What are the reservations you might have about introducing,
Yeah.
olefins and stuff like that into the process?
For what I am working on, I stay away from plastics 100%. They are nasty stuff when they burn. They don't burn the same way as the others. The products that come off of them are things which are tricky and things. So no, it's not. This system is on for a biomass type of thing.
Well, back in the 90s, I was working with a tribe in Arizona with the concept of trying to dispose of tires. And a company up in Wisconsin, Kutrib, had they had water chambers on both ends of the system, and they could feed whole tires in there, and they would pyrolyze them, and they would recover the oils and use the gases to heat the system. And they came out with, I guess, activated carbon and steel belts, So
I would say they did not get activated carbon. They're getting carbon black.
yes, thank you. Good correction. 30 years ago, it was hard for me to remember carbon black on the spot.
Yeah. So because the cellular structure and stuff of carbohydrate biomass is what contributes and makes it so that we're getting biochar, whereas the carbon atoms, which are found in abundance in tires or in oil for that matter, if you burn it, you're not going to get biochar, you're going to get carbon black if you've got some, if you didn't burn the carbon all the way down. So biochar relates to the biomass very, very specifically. Same way with plastics. It's going to give you other stuff. It's not a biochar.
Yeah, I think my understanding of biochar after reading Albert Bates's book, Burn, remember Albert was at the June 2019 Carbondale event.
Yep.
There's a lot of different ways to make biochar, and whatever you're going to get out of it depends on what you put in and how you produce it, the temperatures, the equipment, everything. It's so every time you want to make something, you're going to have to plan out this process. Yeah. I mean, that's how I understand it. So you're going to get biochar you don't want for some, that you're not going to put in the soil sometimes, but maybe you can put it in concrete and sequester it that way.